Hello everyone, I'm Pinji Chen from Tsinghua University. Today, I'm delighted to present our research, cross-origin web attacks via HTTP2 server push and signed HTTP exchange. The same origin policy is a cornerstone of web security, designed to prevent malicious scripts on one website from accessing data on another, thereby safeguarding user data against cross-origin attacks. We all know that SOP is URI-based, which means that two resources are considered to have the same origin only if their protocol, host, and port URI tuple are the same. However, we discovered that recent advancements in the ATP protocol undermine the same origin policy, broadening the SOP to SAN-based. Specifically, we identified two server delivery mechanisms, ATP2 server push and signed HTTP exchange, that, according to their specifications, treat all domains listed in the subject alternative name of the certificate as the same origin. SAN-based origin is more permissive than URI-based origin. Prior research published at the CCS conference has shown that 96% of certificates contain multiple domains in their SAN list, and notably, 3.2% include domains belonging to different organizations. This implies that a SAN-based origin may contain disparate entities. When this relaxed origin policy interacts with the mechanisms we introduce, it may pose security threats. Server push and SSG can specify other origins in the shared certificate, for instance, via the authority pseudo header. This allows attackers to push or provide assets to other origins listed in the SAN, even if those origins are held by other organizations. Based on these findings, we propose two novel attack vectors, cross-push and cross-SSG. An overview of these attacks is illustrated in the figure. First, we assume that the attacker can acquire a certificate that is shared with the victim's website. Second, the attacker will lure the victim into clicking a malicious link. When the victim visits the attacker's website, the attacker uses HTTP2 server push or SSG to deliver a script resource and cite its origin to the victim's website. Due to the relaxation of same origin policy, the browser will accept malicious cross-origin sources as same origin and execute them when loading the victim's website. This ultimately leads to cross-site scripting, cookie manipulation, and other exploitations. Notably, our attacks introduce new security implications. In prior work, attackers who obtained a certificate typically could only launch man-in-the-middle attacks. In contrast, our attacks enable off-path attackers to launch practical web attacks using a shared certificate. Next, we discuss the practicality of our attack. We will address the following three questions: how to acquire the shared certificate as an attack condition, how to extend attack duration, and how to bypass potential countermeasures, such as the victim revoking the shared certificate. First, acquiring a shared certificate is the primary prerequisite for executing our attack. We discovered that there are no mechanisms to ensure that the certificate owner and the domain owner remain aligned. Therefore, we propose two methods to create attack conditions: domain reselling and domain takeover. In terms of domain reselling, attackers can buy numerous domains and issue a multi-domain certificate for them, and then resell part of the included domains to victims while retaining the shared certificate. In terms of domain takeover, it occurs when domain names point to deprovisioned VPS IPs or expired domain names. Since these targets are publicly available, an attacker can register these abandoned services, reconfigure their DNS records to point to attacker-controlled infrastructure, and issue the certificate via ATP mode. Finally, the attacker can use this method to obtain a shared certificate that includes the hijacked domain names. The duration of the attack is another critical factor influencing its practicality. Traditional domain takeover attacks will be invalid after the dangling DNS record is removed by the victims. In contrast, our attack is still valid after the dangling DNS record is removed until the certificate expires, which typically takes 398 days. However, our findings reveal that a user-friendly mechanism known as domain validation reuse can potentially extend the attack duration to 796 days. This mechanism allows the certificate applicant who has previously passed domain ownership validation to skip revalidation when applying for a new certificate within a specific time frame. This period can last up to 398 days. So, the attacker can reapply a new certificate on the last day before certificate expiration, extending the attack duration from 398 days to a maximum of 796 days. A potential countermeasure against our attack is to detect unauthorized certificates via city logs and revoke them. However, we introduce a strategy that makes an illegitimate certificate irrevocable. To revoke a certificate, one of the following two conditions must be met. The issuer should pass domain ownership validation for all domains included in the certificate or possess the private key. Now, consider what happens if an attacker issues a shared certificate that includes both the attacker's domain and the victim's domain. Unfortunately, the victim does not meet either revocation condition. We also conducted an experiment on ZeroSSL to report an illegitimate certificate shared with our domains on the official problem reporting platform, but no reply. To evaluate the impact of our attack in the real world, we conducted a large-scale measurement. On the client side, we measure which browser accepts server push and SSG. Our test targets include top-used browsers on state counter, default browsers on leading mobiles, and celebrated applications on the App Store. On the server side, we measure which website allows attackers to acquire a shared certificate, including resilient domains and dangling domains in Tranco top 1 million domains. In addition, we measure the existing third-sharing domains in Tranco top 1,000. Measurement results show that vulnerable browsers are widespread, where the latest version of 11 top-used browsers and 5 default mobile browsers are vulnerable to at least one of our attacks. We think that security threats to mobile browsers are more severe since mobile browsers contribute more traffic than desktop browsers. Meanwhile, we surprisingly found that some celebrated applications used built-in browsers based on the mobile OS web view component, which inherited the same vulnerabilities as web views. This significantly extends the attack surface from browsers to third-party applications. On the server side, numerous websites are affected. Some cases even affect notable websites. For instance, ftstatic.com, which ranks 3,895, was once resold from an Australian food company to an American advertising agency and could potentially be exploited by the original domain owner. A subdomain of windowsupdate.com from Microsoft is dangling, which can be registered by any attackers. Moreover, many top-ranked domains share certificates with low-ranked domains. These low-ranked domains are even from different organizations, which is confirmed by Baidu.com. To mitigate our attacks, we propose the following countermeasures. For browser vendors, they should enforce consistent authority checks in browsers to mitigate cross-push, and enforce single domain certificates to prevent cross-SSG. For certificate authorities, we suggest they provide a mechanism allowing domain owners to remove their domains from issued shared certificates. For users, they should regularly inspect certificate status in domain registration to detect unauthorized shared certificates. We also responsibly disclose our findings to affected vendors and receive positive feedback from Huawei, Baidu, Microsoft, etc. To sum up, we observed that HTTP2 and HTTP3 SAN-based origin is more permissive than browser URI-based origin. Based on this finding, we proposed two new cross-origin web attacks, cross-push and cross-SG. We demonstrated how to leverage the weakness in web PKI to facilitate our attack and conducted a large-scale measurement. The result shows that our attacks affect top used browsers such as Chrome and Edge and notable websites, including Microsoft and Baidu. You can scan the QR code below to see our attack demo. That's the end of my presentation. Thanks for listening. I would also be happy if you could contact me for further communications. Thank you.